Hello and welcome to NEIWPCC's UST Inspector Training Webinar Series. My name is James Plummer and I'm going to be moderating today's session. I'd like to introduce our presenters today. First up at bat is Ryan Haerer, Program Analyst for US EPA's Office of Underground Storage Tanks. Ryan's been working in EPA's Office of Underground Storage Tanks since 2013 in the Release Prevention Division, with his primary emphasis as the point of contact for solving emerging national issues that often arise when we introduce new fuel blends into old infrastructure. He has an MA in International Relations and Economics with a specialization in energy, resources, and environmental policy from Johns Hopkins School of Advanced International Studies after completing a degree in international development at Ohio State. Prior to school, he served in the U.S. Army from 2004 to 2007 and is currently completing an MA in National Security Studies. Following Ryan is Doug Hansen. Doug has spent the last 10 years managing Utah's underground storage tank compliance section. He has served 2 years as the Region 8 representative on the ASTSWMO Emerging Fuels Task Force. Prior to his current position, Doug spent 13 years overseeing cleanup of UST releases in the Utah Petroleum Storage Tank section and 1 year on special assignment working on development of the Western Climate Initiative. Doug has a Bachelor's of Science in Chemical and Fuels Engineering from the University of Utah. Ted Unkles is also with us today. He's the UST Program Coordinator for the Vermont Department of Environmental Conservation. He is the state coordinator for the UST program. He's worked in Vermont's UST program for 29 years, beginning as a field inspector in 1990. In addition to his UST duties, Ted is a member of the DEC Spill Response Team, and he is also a member of the Vermont Hazardous Materials Response Team. Ted has a bachelor's degree in earth science and a master's degree in natural resource management. Ted also serves as the chairman of the select board of the town of Bradford, Vermont. Since the town has an underground tank containing diesel fuel at its highway maintenance garage, he occasionally gets to view the UST program from the point of view of the regulated public. Additionally, we have Dr. Chris Marks, an associate environmental scientist with the Arizona Department of Environmental Quality. Dr. Marks recently joined the UST program after a postdoc appointment with US EPA's Office of Research and Development and obtaining his PhD from the University of Oklahoma. His expertise is in hydrocarbon biodegradation and microbiologically influenced corrosion in both upstream and downstream oil and gas systems. Currently, Chris serves as a UST remedial project manager and a senior scientist investigating mechanisms of UST biocorrosion, prediction, and mitigation. Additionally, here is a quick overview of what will be discussed today.
Okay, I just got a message on my computer that says I'm the presenter, so presumably, I hope everybody can hear me. Thank you all for coming. This is, I think this is an incredibly important topic. As James mentioned, I've been in the UST regulatory field for almost 30 years now, and emerging fuels certainly are creating some challenges that we did not see back in the early days of the program. So this, I hope, will get people up to speed a little bit. The way we got started in this was the Renewable Fuel Standard, which was part of the Energy Act of 2005, signed into law by President Bush. Initially, it required 4 billion gallons of renewable fuels be added to our fuel supply back in 2006, and there were intermediary goals in there, but it maxes out at 36 billion gallons of renewable fuels in 2022. So we are adding a lot of renewable fuels to our fuel supply, and there's more still to come. Now, I just talked about renewable fuels, but this topic here is emerging fuels. So what exactly is an emerging fuel? any conventional fuel that's been blended with a renewable fuel. For example, gasoline that's had some ethanol added to it, the E10 that we see all over the place. Biodiesel blended into conventional diesel fuel. And the other thing that makes a fuel an emerging fuel is any conventional fuel that has had its formulation changed very significantly. Probably the most notable one is ultra-low sulfur diesel fuel, which is still petroleum-based fuel, but not too long ago, the sulfur content went from 500 parts per million down to 15 parts per million, and that did result in a change in the chemistry and a change in some of the characteristics of the fuel. So what are some of the problems we see with new fuel formulations? This, I will be the first to admit, this is a very, very, very oversimplified view of things. It's a highly complex subject, and I'm just going to go over this really quickly. But ethanol reacts with oxygen to form acetic acid. We all know if you leave some wine out overnight, it turns into vinegar, and that's the same sort of thing that can happen with E10 gasoline. Ultra-low sulfur diesel tanks that contain that, we're seeing some very severe corrosion in the ullage portion of the tank. I myself don't know exactly what's causing that. I'm not sure if others do, but I mean, that's certainly something that's interesting going on. Biodiesel has all kinds of bizarre chemical reactions going on. It oxidizes readily and it forms aldehydes, alcohols, lots of different organic acids. There's some very complex chemistry there. And the other thing that I didn't mention was that we're also seeing microbial-induced corrosion. That is, some of these new fuel formulations provide a suitable habitat for little microbes to actually live inside the tanks. And those microbes produce waste products that can sometimes be corrosive. So that's just a really, really quick summary of some of the headaches we see. So with ultra-low sulfur diesel, this is some of the problems that we see. This photo was sent to us courtesy of our friends in the New Jersey Underground Tanks program. But this is the shaft of a submersible turbine pump, and you can see the corrosion that's occurring on that steel shaft. Ethanol added to gasoline. This is another photo that was provided by our friends in New Jersey. There's lots going on in this sump. If you look at the very bottom, you can see that the EnviroFlex pipe has badly delaminated. The plastic coating is completely gone. Obviously, the steel portions are corroding badly, and the copper tubing has that nice blue coating, which I can't remember if that's copper acetate. Can't remember exactly what it is, but there is a chemical reaction that again is from the acetic acid. So we all know that EPA and state rules require that underground storage tank systems be compatible with the fuels they store, and that's all fine. Obviously, a tank has to be compatible with the E10 gasoline or the biodiesel blend that's in there, but the rules don't address compatibility with the decomposition products, with the acetic acid and the alcohols and the aldehydes that I mentioned that form with biodiesel. So we're finding that our underground storage tank systems are sometimes containing some substances that nobody ever really anticipated would be in there. We've got organic acids that are causing corrosion. We've got filters in dispensers that have become clogged with glass fibers from fiberglass tanks. Not exactly clear what's causing those resins to break down, but it's very obvious if the fibers are being drawn up through the pump that something is causing those resins to break down. So what's where do things stand now? Well, the good news is we haven't yet seen any major releases that we can attribute to corrosion and system failures caused by these formulations. But there is a concern that the tsunami might be coming just over the horizon, that we might start to see in the very near future a whole spate of new releases caused by this corrosion. So all of us regulators, cleanup professionals, tank contractors, owners, operators, we all need to be aware of what these issues are and some of the things that we can do to address them. So one of the things that we need, obviously, is more and better data on what's going on. And the ASTSWMO Emerging Fuels Task Force has constructed some really good tools for reporting some findings as well as tracking compatibility. Later on in this webinar, you'll be introduced to the corrosion observations tool, the compatibility tool, and the compendium. So that's some important stuff that's out there. So that's a really, really quick overview of how we got where we are and what the situation is that we're currently facing. There are others in the webinar who know these issues in much more detail than I do and who I think will go into better detail. Thank you all very much, and on to the next presentation.
Awesome. Thank you so much, Ted.
Well, thank you, Ted, for the great introduction. I'm Ryan Haerer with EPA. I'm going to start off by focusing on the basics of the compatibility requirements in the federal regulation that are intended to help prevent some of those issues that Ted just showed us. So since 1988, the federal UST regulation has required protections for both that compatibility and corrosion he mentioned. And the way to think about it is that generally external corrosion, or our corrosion protection requirement is generally for the outside of systems. The way Congress set up our rule, the federal statute actually allows EPA to only require corrosion protection for components in contact with the soil, so on the outside of systems, the metal components. Compatibility, on the other hand, is basically dealing with the inside of the UST systems. The 2015 regulation had some new compatibility requirements. I think something that is really interesting that I want to emphasize that Ted had said is that incompatibility with not the fuel, but the remnants of however that fuel changes when you start getting some microbial action in there. So it's an interesting thing. You'll hear a lot more about that today. So all these requirements that I'm talking about are really important because UST systems are made to last a very long time, 30 years or more. Equipment's generally made based on the fuels that are in use at the time that it's constructed. But of course, during the life cycle of an UST system, these fuels change while that infrastructure has to stay the same and adapt to whatever fuel comes into it. So this slide shows a few examples of changes just in the last 20 years or so. First, MTBE was found to be bad, so we started using ethanol as an oxygenate. But then the renewable fuel standard, for technical and policy reasons, Ted mentioned that on his first slide, required putting way more ethanol and biodiesel into the fuel supply. Separate from the increased biodiesel requirement under the renewable fuel standard, different air quality rules required that diesel itself became cleaner. That required removing the sulfur from the fuel, which also then required other technical changes to the fuel chemistry to adopt to the lower sulfur. And this happened in stages, with the last being around 2006, which happens to coincide with a timing of a lot of corrosion that we started finding in these diesel systems, which you'll hear about today. So interestingly, right now, you may hear something, this doesn't really apply to the tanks program as much, but the shipping industry is actually going through a transition next year, similar to land-based diesel fuel, that requires the fuel to become cleaner. So there actually may be some supply and demand impacts on our land fuel supply for biodiesel. So if you hear about the International Maritime Organization, you might be interested in hearing about those changes. And the final complicating factor about each of these fuels is that our fuel system sometimes allows small amounts of these fuels to mix into the other ones where they don't belong. So there's enough changes that we've seen with each one of the fuels by itself, but then we double that issue with changes when you put each of the fuel mixing into the other fuel supply. So this is an unneeded but real headache that we're seeing in the fuel system today with our problems. And the other presenters will go deep on what these changes do to that infrastructure. So here's a couple examples. You saw some from Ted with the corrosion. These are what we would consider incompatibility or compatibility issues. Things just generally become harder, softer, or shrink, or they swell. So we have special rules in place in the federal UST regulations to prevent whatever fuel is stored from doing that to those pictures that we just saw. The 1988 regulation required us to be compatible with the fuel or whatever substance they store. We knew in 1988 that was a very important thing to think about. But based on 25 years of US system experience and some of those fuel changes that happened in that time, the 2015 regulation, the most recent update and the only major update to the federal UST regulation since 1988, it added 3 additional requirements to that base compatibility requirement, but only if you want to store biofuels with more than 10% ethanol or with more than 20% biodiesel. So that would include E85 or E15. Those fuels have properties that can make them much more aggressive towards the UST system materials. You'll hear a lot more about that today. So here are the requirements. The first was a requirement to notify the implementing agency 30 days in advance of switching to storing one of these fuels. This gives the owner and the agency a chance to meet what you'll see in number 2 before you actually start storing the fuel. You don't want to store the fuel and then try to determine compatibility in case it's incompatible. So that second requirement is that you have to demonstrate the UST is compatible with the fuel stored. Or you can use an alternative option determined by the implementing agency to be no less protective in the environment. However, as EPA, we have not allowed an alternative option. I don't think most states have done that either. The third requirement is that you keep records of this compatibility documentation for as long as the fuel is stored. So currently, states are in the process of updating their regulations to be no less stringent than the 2015 federal UST regulation. So in doing that, a lot of them are implementing new compatibility regulations right now. So in the federal regulation, these are the components from which you must demonstrate compatibility: tanks, piping, containment sumps, pumping equipment, release detection equipment, fill equipment, and overfill equipment. So contrary to many press releases and news articles and things you hear in the trade press, it is not just about adding blending pumps or compatible dispensers, or it's not just about having tanks that are compatible. To meet the federal regulation, you have to make sure each of these things on this list is compatible. So you can demonstrate compatibility for each of those components one of 2 ways. The first, you can show that the equipment is certified or listed by an independent testing laboratory, such as Underwriter Laboratories. You're all very familiar with that. ASTSWMO has created a tool to help you find those listings. You'll see a walkthrough, hear a little bit more about that later today. The other option is, that applies to this next thing. Another option to demonstrate compatibility is written approval from the manufacturer of the equipment or component that affirmatively states that it's compatible with the fuel stored and specifying what range it's compatible with. So ASTSWMO has a tool to help track these compatibility statements from manufacturers. So to meet and check this compatibility requirement, it actually takes 2 steps for each of those things on the list. First, you have to determine what manufacturer and model number of the equipment is in the ground if you're going to get the correct UL listing or manufacturer statement. It seems like a no-brainer, but we've actually had that happen on several occasions where people give us a UL listing, but they haven't identified what type of component they have that they're listing it for. So we kind of say, how did that work? So through compliance assistance, we've seen a lot of things happening as we started implementing this rule. You guys will probably have already seen a lot of these in your own state similarly. So it's critical to remember that when storing any regulated substance, beyond those things on the list, the whole system has to be compatible. This has been a requirement, like we said, since 1988. So this is where it gets interesting. Pipe dope and sealants are not on that list of components that has to be demonstrated to be compatible, but they are required to be compatible with the substance stored since they're part of the USD system, and all parts of that system have to be compatible. We got a lot of questions on this in the last 2 years. EPA AST has put up a couple of questions and answers on this on the 2015 UST regulation technical compendium. And just to pitch for that while I'm here, we have put a lot of interpretations. I think maybe around 30 or 40, maybe even more questions and answers that we've made some interpretations after people have had some questions about that regulation. So in regards to pipe dope and sealants, the 3 points to keep in mind that if a station that you're looking at is going through this process to demonstrate compatibility with all these other components, you want to think about the pipe dope and sealants. That pipe dope must be compatible. There are multiple versions, just like with all other components, available in the market. Some are intended to be stored with certain fuels and some are not. Some are soft set pipe dopes which can degrade, if they're with ethanol or biodiesel that's of too high of a blend. And the third thing to remember is that these high ethanol compatible pipe dopes were not around or available in the market until 2007. So since most of these connections are underground, where resealing those joints would require excavation, when you're inspecting them for compatibility or looking at these paperwork at an older system, you'll want to look carefully to see that the owner is meeting the compatibility requirements. Since those compatible dopes were not available until 2007, you have to really look and ask and make sure that that system is actually intended to store the fuel that they're asking to put in it. So to wrap up, I want to discuss something very important that you can use to help solve these problems with corrosion and compatibility at the national level. So you'll hear about it today, but ASTSWMO is now tracking corrosion and degradation related failures in UST systems. In that system, you can upload your own observations that you see out in the field into this tool and help solve these issues across the country. And what I mean by that is that this data on national problems from incompatibility and corrosion is generally not available in a data set either from stations or compiled nationally for us as regulators. Although some states have done, small time period studies on particular issues, and you'll hear about this after a great one that's currently ongoing from Arizona, we generally don't have data sets that we can write papers or make recommendations or write guidance based on because the information we have is anecdotal. So as a federal agency, we have to base all our work on scientific data, something that's published. And so this ASTSWMO tool, we hope, is a method to collect that data and put out a report that then we can use as a scientifically based piece of information to help address these issues at a national level. So volunteering for that will be really helpful. You'll hear a lot more about that today. So with that, I'll turn it over to the rest of the team to take you into the rest of the webinar. Thank you.
Awesome. Thanks, Ryan. And now we will pass the torch on to Chris. You all set to go?
All right. So I'm here presenting today with my colleagues Tiffany Yee and Tara Rosie, and this portion of the webinar is going to be focusing on an ongoing study we're undertaking here in Arizona to assess the health and integrity of our UST infrastructure here and some of the preliminary findings emerging from this study. So as we've heard, so far up to this point in the webinar, there's been a lot of changes to the fuel landscape over the last 20 years, and these chemistry changes have also resulted in an increasing awareness of internal corrosion issues within our UST system. So at this point, I just want to briefly highlight 3 landmark studies raising this awareness, starting with a PEI survey released in 2010, in which 42% of respondents across North America reported increasing equipment issues relating to the storage and dispensing of ultra-low sulfur diesel, and those were from components all the way from the storage tank to the dispensing equipment. A few years later, in 2012, the Clean Diesel Fuel Alliance released a study identifying microbiologically influenced corrosion, or MIC, as the primary corrosion mechanism causing tank degradation in diesel storing systems. And most recently, in 2016, the EPA released a study identifying widespread internal corrosion inside diesel USTs, and this was identified using the CRC corrosion rating system. And so here in this figures at the bottom of the slide is on the left a reproduction of the data from their study summarizing their corrosion system with 3 levels of minimal, moderate, and severe, and showing that the study included tanks of both steel and fiberglass construction, highlighting that the majority of tanks examined in this study, which was conducted across various locations in the U.S., exhibited moderate to severe corrosion. And you can kind of see some of the images here that were lifted from that report on the right, with a generalized corrosion observed throughout the surface of this STP riser and aggressive corrosion attacking the metallic infrastructure from the tank bung. So here in Arizona, we wanted to undertake a similar study to evaluate, as I said, the integrity of our open UST universe. And so to do that, we employed a study that evaluated the internal corrosion on the internal UST surfaces and the internal infrastructure. So this included both diesel and gasoline storing systems with tanks of both steel and fiberglass construction. Throughout this study, the data that was collected included internal visual inspections by video, which were used to assign corrosion ratings that I'll talk more about here in just a minute, ullage characteristics, including temperature and relative humidity, testing for the presence of water, and laboratory analyses of water bottoms and fuel samples where they could be obtained. So as you can see, if we think about the corrosion triangle, the classical corrosion triangle, and how this study links up to that, where you have a susceptible material, the presence of an electrolyte, and electrochemical potential that's derived from these changes in fuel chemistry and those chemistry changes as microbial degradation occurs, those factors come together and result in the corrosion we all too often see. So on the note of corrosion and how we assessed it in terms of a rating scheme, in ADEQ study here, we came up with our own rating system based on examining the internal surfaces through those visual inspections. And our rating system is in 4 categories, A through D, getting progressively worse. But there's also a correlation, and we applied this the CRC corrosion rating system, which has the 3-tier that I mentioned earlier, the minimal, moderate, and severe, which uses the STP shaft as the sentinel infrastructure for corrosion rating. And you can see that these are related based on corrosion coverage area, and we'll be talking more about that and their relationship in these corrosion rating systems in the following slides. But first, a look at the Arizona UST universe. Currently, there are over 5,700 open USTs in the state of Arizona, and that's just far too many for us to interrogate each tank individually to investigate the total universe health. So we looked for a representative subset and found that through a partnership with our school systems. So far in our study to date, there have been 78 school tanks that were studied and received a rating, and these were from locations geographically distributed across the state. So for anyone who has not visited the state of Arizona yet, it's more than just the Sonoran Desert that we have here in the Central Valley that everybody tends to think of. There's actually some high mountain areas in various parts of the state, so we have a good distribution of climatic differences depending on which part of the state you're in. So as I mentioned, this was these school tanks are a representative subset, and we can see that looking at 2 metrics here. The first on the top right is an age distribution of the USTs, In green in this box and whisker plot, you can see the statewide open USTs. You can see brand new tanks that are going in, all the way up to some that are getting very old, now approaching 70 years old. And then in blue, you can see the age of the tanks so far studied from our school partners. And you can see that this is a subset of the bulk data representing the statewide universe. Down here on the bottom left, you can see a material type breakdown in the comparison on the left with statewide and school tank study on the right. So here in Arizona, you can see we have predominantly fiberglass tanks. Statewide, we also have some composite steel fiberglass, and then shown in blue there is steel. And if you look at our school tank study, we again see a bias in our sampling towards fiberglass as representative of the state and steel. So from this data, we're confident that by studying these school tanks, we're getting a representative data set to assess the health of the Arizona UST system. So let's look now at the tank ratings and using some visuals to kind of put together images of how our rating systems work. So for the next several slides, what you'll see is across the top, a tank rating, in this case A, and then the corresponding CRC rating that would accompany that, so in this case, minimal. So under this rating, this would be tanks that you see no issues, no cracking, degradation, oxidation, etc. And so here in this case, in our study, only one tank received the rating of A. It's a 22-year-old fiberglass tank here, and as you can see from the image on the left, the walls and end cap are completely clean, and on the right, the ball float is completely free of oxidation. So if we move now to a tank rating of B, also getting a CRC rating of minimal, this is where you're going to start seeing some degradation issues pop up. This would be in the form of blistering, deformation, oxidation, etc., but this is going to be limited to less than 5% of the tank surfaces. So on the top left image here, you can see a 26-year-old steel tank in which the walls are predominantly clean, but you do see some generalized oxidation occurring in the top right of the tank there. On the left, there's a fiberglass tank that's 30 years old that is predominantly free of defects in the walls, but you do see product buildup there along the tank walls above the liquid line. So in the bottom here, just some images of minor metallic oxidation occurring on tank bung and ball float infrastructure that would count as part of the minimal or tank rating of B, is what you'd expect. Now, as we progress to more severe tank issues, this would be a tank rating of C or a CRC rating of moderate, so we're getting worse as we go through here. Now you should see heavy flaking and blistering, degradation, maybe some minor cracks in the walls. Ideally, though, these are going to be less than 50% of the tank surfaces. So in the top right photo here, you've got a 39-year-old tank in which you can see generalized oxidation along the tank wall and some along the end cap, whereas in the bottom center, you've got a 34-year-old fiberglass tank with lots of blistering and flaking occurring on the end cap, and somewhat less so there on the tank wall, with a zoom-in picture in the top left showing kind of what that blistering looks like up close. Finally, for the worst-case scenario, here's tank rating D, CRC rating of severe. These are tanks that have just severe issues of blistering, delamination, cracks. You can see in these images, this is going to be over 50% of the tank surfaces are going to be impacted by these issues. And on the left there, this is the same tank on top and bottom. You can see just extensive delamination and flaking of the fiberglass walls all throughout. Same thing on the bottom right with a 28-year-old tank. Interesting to note here on the top right is a 27-year-old tank which has been lined less than 2 years before this picture was taken, and you can see that the tank liner has just completely been compromised with penetration up in the top center there, and then the tank liner, as you can see, is pulling away from the wall itself, so it's just completely failed at this point. So these tanks are the worst case scenario and definitely warrant investigation to determine whether releases have occurred or not. So that's kind of the visual association of what our rating system looks like and how it relates to the CRC mechanism or rating system. So now let's look at the preliminary results coming out of this study so far, starting on the left with a global breakdown of the tank ratings observed. As I mentioned in the beginning of this section, there are 78 tanks rated to date, and 71% of those received the B rating, so that's where issues were noted on less than 5% of the tank surfaces. I do want to point out that almost 30% of the tanks rated so far exhibit moderate to severe ratings. If we look now at the age distribution on the right through these box and whisker plots within each corrosion rating, you can see that for the B, C, and D ratings, there's no statistically significant difference between the median tank age within corrosion rating, and so tank age is not predictive of corrosion rating. I also want to mention that for each tank studied, the internal inspection video was used to assess the ADQ corrosion rating and the CRC, and so what we found was about a 71% agreement between the two rating systems. And as I noted earlier, the EPA study predominantly used the CRC rating system. So this shows that there's agreement between how these ratings are assigned and that there's comparable results obtained between the two studies. Looking more deeply now, by corrosion rating by fuel type on the left, we studied both diesel and gasoline systems, as I mentioned. And one thing I just want to point out is that you see moderate or severe in both fuel storing systems. And same thing as you see on the right with tank material, fiberglass and steel. Again, noting that both systems do exhibit moderate or severe corrosion. So building upon the studies that were mentioned earlier, we can see that moderate and severe corrosion issues are not exclusively limited to one type of UST system by construction or fuel type. Each of these is susceptible. Now, I do want to note that there is a disparate sample size between these subgroupings, and so while I'm highlighting these distinctions, they're not sample sizes are not yet large enough to codify them as distinct, and so we will be continuing this study to increase the sample size. Finally, for the results, looking at the tank ullage characteristics, specifically relative humidity, on the left is a distribution of the tank humidities encountered in our Arizona school tanks project here in green, and the EPA study in blue. And unsurprisingly, we see that there's lower humidity here in the desert state of Arizona, but we do have that wide distribution for the other climates that we encountered throughout our statewide sampling. I do want to point out that the EPA study was conducted at several locations across the United States, and so there too you see a wide distribution, but a disparate grouping of humidities encountered between the two studies. On the right is a scatter plot where on the x-axis we have relative humidity encountered in the tank, and then on the y-axis are the corrosion rating systems assigned to them. And I don't want to read too much into this figure, but what I do want to highlight is despite the differences in distributions between the humidities observed in tanks between the two studies, what you do see is that there are examples of tanks with minimal all the way up to severe or B all the way to D corrosion rating. So taken together, this data shows that one, ambient relative humidity has a strong influence on tank ullage humidity, and this should be no surprise given that they're vented to the atmosphere. Also, that relative humidity in the tank ullage, in this case, shows no or a weak positive correlation with the tank corrosion rating. So Spearman's Rowe ranked correlation coefficient for the EPA study is weakly positive, whereas in our study here in Arizona, there is no correlation. So at this point, we can say that tank relative humidity in the ullage is not predictive of internal tank corrosion status. So finally, looking at some key preliminary findings that are emerging from our study is, first of all, corrosion of internal infrastructure within USTs is widespread and common. In our case, 99% of the tanks that we studied exhibited some evidence of degradation, with almost 30% what we would classify as moderate to severe. So this is in line with what was observed and reported in the EPA study, which looked at diesel storing USTs. In our study, we also want to emphasize that this is occurring in both diesel and gasoline systems with tanks of steel and fiberglass construction, all being susceptible to moderate or severe degradation. So these again expand upon the findings of the EPA and Clean Diesel Fuel Alliance studies, showing that the corrosion observed within these tanks is occurring on the walls as well as the internal infrastructure necessary for tank functioning. Also, I want to influence that MIC, or microbiologically influenced corrosion here, is a very complex process, as you heard a little bit about earlier on in the webinar. So we showed here so far that median tank age and tank relative humidity in our study are not significantly linked to be predictor variables for tank corrosion status. This is also in line with the EPA study, in which 28 potential predictor variables were assessed, and no single variable was identified in that study either. So MIC is a complex process, and it warrants further consideration to understand the linkages between fuel degradation issues and tank fouling and ultimately corrosion and degradation. So finally, here at ADEQ, we are continuing this study, and we strongly encourage our tank community members to undertake similar investigations in other states, and this all feeds together to provide data that can also be entered into the corrosion reporting tool that you'll be hearing about in the next portion, and really kind of gain information to put together a snapshot of understanding and a good data set to tackle this national issue. And so with that, I'll close out my portion with my contact information and the references to the 3 studies I highlighted earlier for anyone interested in investigating them, and I'll hand it off to Doug.
Awesome. Thank you, Chris.
All right. Good morning, everybody on the West Coast, and afternoon for those of you on the East Coast. Thanks for attending this afternoon. As was introduced, my name is Doug Hansen, and although I'm the manager of the Underground Storage Tank Compliance section here in Utah, I'm here in my role as a member of the SWMO Emerging Fuels Task Force, as is Ted Unkles, who you heard from earlier. For those of you that might not be familiar with what a SWMO is, it's the Association of State and Territorial Solid Waste Management Officials, and it's an organization that basically exists to make the life of state regulators and territorial regulators easier. It's broken up into different subcommittees, including the Tank Subcommittee, which is where the Emerging Fuels Task Force falls. We are made up of state and territorial representatives from each of the EPA regions, and our specific purpose is to help states adjust to the changing fuels in our market, and particularly the ethanol and biodiesel blends that we've been talking about today. And today I want to talk about a couple of tools that you've heard referenced in several of the presentations, if not all. First of all, we'll be talking about this corrosion observations tool that we developed a few years ago, and then this compatibility toolkit, which has been live just a little less time. The link listed there, if you go to that, you will see a page that looks like this. You'll see both of the tools listed at the bottom, and below where the screenshot is there, you'll find links that actually take you down into those tools. First off, I want to talk about the corrosion observations tool. And really, as we've talked about today several times, it's becoming critical for us to find a way to gather data and report the observations that we're making and seeing as we are conducting inspections. And that's the primary purpose of this tool, is to start that process. And then hopefully as we do that, we're able to start identifying some trends and highlight and identify possible research opportunities so that we can further evaluate what we're seeing in the field and turn it into something useful. Also, this is an opportunity for us to create a repository of information that can be used for training, and not just for inspectors and people who are going out from a regulatory perspective, but owners and operators of UST systems as well. We find that as they become better educated as to the risks that they're facing, they change behaviors and adjust to the challenges that the markets are providing. And then obviously our overall goal is to prevent corrosion-related releases from UST systems. So when you get into the corrosion observations tool, and again, the link for that is on the left-hand side of your screen there, you'll see this page, and this is where you'll be able to report what you're seeing. And I want to go over just briefly the pieces of information that you should be prepared to provide when you're uploading something that you've observed in the field. So first of all, we're going to ask for some identifying information. We need to know your name, who you're working for, and your agency. We'll accept information not just from regulators, but if petroleum marketers or retailers have information that they're comfortable and willing to share, we'd love to get that as well. So let us know who you are, who you're working with, and some way to contact us if we have questions. And this is the foundation for the credibility of the report that we're going to be producing. We're also going to need some facility information. We need to know where it is, and we are only looking at city and state. I know some people are a little uncomfortable providing the facility name or some specific details beyond that, but this at least lets us know regionally where we're gathering information from, so that if that becomes a part of the trend, we can make those observations and determinations as well. We need to know what component of the tank has been affected and the degree of corrosion. And you can see the tank components listed there that are specifically part of the reporting tool, including the catch-all at the bottom of other connection points. And I want to show you what that tool actually looks like, because it's fairly easy to report here. So first of all, this is what you'll see on the screen. You see 3 images that show degrees of corrosion. And our point in providing that is we realize that there's a great deal of subjectivity involved with making a report like this. And hopefully by showing what low to moderate corrosion versus significant or severe corrosion looks like right on the tool, we can eliminate some of that variability and be a little more consistent in how we're reporting these things. Once you've determined what the degree of the corrosion is, then you go down and select that in the corresponding component of the system below. So it's just a checkbox. So fairly easy and straightforward to report. Additionally, as far as facility information goes, we need to know how long the component has been in use. We realize that information may not be available or may not be known, so there is an unknown option there. But to the best of your ability, if we can estimate the life of that component, that helps us start grouping by age as well. We'd like to know whether or not there was actually a release from the component. Was it just observed corrosion, or did it cause a problem? And then we need to know what the fuel type is. Is it ethanol that's less than 10%? Is it gasoline with greater than 10% ethanol? Is it the ultra low sulfur diesel that we've talked about? Or is it biodiesel with more than 5% biodiesel in it? And we realize that that's not the universe of fuels that you might see. So if there's something else, please put that, and then there's a comment field if you select other. And finally, we need to know if there was any sort of corrosion protection in place prior to the corrosion being observed. And that could be more conventional methods of corrosion protection, or some of the new tools that are out on the market. And then finally, how was it discovered? Was it just a visual observation during an inspection? Did you have some clogged fuel filters maybe, or other inoperable equipment? It could be that, that we had slow dispensing, or maybe there were some customers that had fuel damage their engines in their vehicles after they fueled up. Those kind of observations are helpful as well. And finally, in the tool, uploading a photo. So you've all seen screens like this before in various settings. Basically, you'll just select choose a file, you'll drill down within your directory and just upload it right from whatever your source is. And we can accept PDFs, JPEGs, PNGs, and GIF files. So any of those formats are acceptable there. So if you want to see what we've collected so far, here is a map of the country. The red states have not submitted anything, and the states that are sort of that grayish blue are states that we have some information from. And just to show you how this looks, you can see New Jersey over there on the right-hand side is one that has submitted some information. And so we're going to go ahead and select New Jersey. You can see it's highlighted in yellow. And also you'll see that underneath the state name on the right-hand side, there are two reports that show up. We're going to go ahead and click on the one that says Homedale, New Jersey. I'm not sure if I'm pronouncing that right. And this is what you'll see. So anybody has access to these reports. You can come in and look and see what's going on in different states and what's been reported. You can see that they're reporting corrosion on a STP that was severe. It was 21 to 30 years old. There wasn't a release associated with it, but it was with regular ethanol fuel, E0 to E10, and that the observation came about just by a visual observation. And you can go through the other states as well and find all the reports from them. And that's that tool. The next tool that we've developed and want to talk about is the compatibility tool. And here are just the references out of 40 CFR 280 that talk about the requirement to document compatibility. And that's what we're trying to do with this tool, is provide a resource for people to be able to do that. So when you click on the link, either from the page I showed you before or use the URL on the left to get to the compatibility tool, you'll see a page like this. And there are a couple of ways that you can access information that's contained in this database, and I'll go through both of those. And really, the point is we want to be able to meet documentation requirements. It's a tool for both UST operators and inspectors. And this is, our vision is that if you go out and do an inspection and the operator does not have the documentation for compatibility, you can show them this website and walk them through it and help them download that information while you're on site, and then they meet that requirement moving forward. So we hope that it's a used tool for not just inspectors, but that you use it to educate your stakeholders in the regulated community so that they can meet that requirement. And also, it's an opportunity for manufacturers of equipment to provide their statements of compatibility so that it's accessible at our fingertips as regulators and those that are our operators as well. So the first way you can access information in this tool is to select the fuel type. And that's going to be either biodiesel blends or ethanol blends. And then you can see here in the example I'm using, we selected diesel blends greater than B20. And then the second step is to actually select the component that you're interested in providing documentation for. And the different options are listed out here below. But in this case, I've gone ahead and just already pre-selected line leak detectors. And you can see after you hit the submit button that you come back with the results of KPS and vaporless having statements in our database. So go ahead and show you what it looks like. I went ahead and selected the KPS, and here's their letter statement of compatibility with biofuel. And you'll notice in that, you may not be able to see it if the print's too small, but it basically says that it's compatible with ethanol E5 to E100 and biodiesel B2 to B100. So they did state the range, as Ryan mentioned earlier. So that's a critical piece of that documentation. So the other way you can find information in this database is by selecting the manufacturer up front. So you go in and you tell it, in this case, I've said, let's look at Bravo Systems. And you can see that we have documentation for their fittings and for their sumps as well. And if you click on the fittings, again, you'll see their statement of compatibility. And again, you can see that they specify the range of fuels. Basically, in this case, they say all biodiesel up to 100 and all ethanol fuels blends up to 100 as well. Now, the other thing that we can do with this tool is we want to keep building this database. We realize that it's not comprehensive or representative of the full universe of equipment that's out there. So we welcome information being submitted. And just as with the submitting a corrosion report, we need to know who's submitting it, what agency you represent, and some contact information if we have some questions. And then provide just a brief description of what the submittal is, what you're documenting with the file that you're going to send to us. And then again, at the bottom of that screenshot, you can see you choose a file. In this case, only PDFs are accepted through this portal. So drill down, provide us with that statement. And we encourage state regulators as you run across information to submit. We encourage manufacturers to provide us information through this portal. And then marketers are also free, and we would love to hear documentation that they have and see that provided as well. And once that comes into us, the information gets vetted. So we do take it seriously and make sure that what we're seeing actually meets the requirements of documentation and is actually relevant and accurate. So that information will be reviewed before we post it and make it part of our database. And that's the compatibility tool. And finally, you've heard us mention the compendium a few times. Back in 2014, ASTSWMO conducted a state survey on emerging fuels. And the data from that survey are tabulated and represented here. You can see by state. You can go through and click through those different tabs and see how different states responded to different questions on that survey. We are looking to update that. We have basically finalized a new survey. So that will be going out, and we'll be requesting information from states in the next few months probably. So we encourage you, as you see that come out, to make sure that somebody from every state responds so that we can get a full data set for the new compendium. So we encourage you to participate in that. We also encourage participation on both of the tools. We'd love to get more corrosion observations. There was a lot of red on that map. We'd like to see more of that shift to that steely gray blue, meaning that more states are participating and sharing what they're seeing in their field, in their states. And then on the compatibility toolkit, please use it and make your stakeholders aware of that. Operators can document their compatibility. If they're struggling to find documentation, they probably can find a good chunk of that on this website, on this tool. And then as you have information and can upload it, please do that as well. And then as you do use both of these tools, we would love to hear your feedback. We'd like to know what's working well, what's not working as well, and how we can improve the tool that we have out there. And finally, I just want to encourage everybody to be part of the dialogue. We're still learning a lot. As we speak, the fuel blends are changing, as Ryan pointed out. The approval of the addition of up to 15% ethanol is becoming a standard in some places, and I think this is going to continue. So please be part of this discussion and provide us feedback. With that, we'll turn it over to the moderator.
Alrighty, thank you, Doug. If anybody has any last-minute questions that they'd like to throw up here, I'll add those to the mix as well. Alrighty, so first question that we got, pipe dope, and just for reference, I am not an expert in tanks, so if I misspeak or anything of that nature, please correct me. And I'm not sure who these questions are directed to, so for any of our presenters, please speak up at will. Pipe dope and sealants are not included in the federal definition of an UST system. Is it an EPA policy to include them in the definition?
This is Ryan Haerer from EPA. So I'll point him to the language that we have in the technical compendium. We have 3 questions specifically answering questions on that. So it's a part of the UST system. Thanks.
Awesome, thank you. Is there any data on switch loading? Was there any evidence of ethanol in the diesel tanks?
So this is Chris from Arizona. Actually, yes, we observed a tank that had, it was diesel fuel that contained over 2,000 ppm ethanol. So yeah, just in our data set alone, there was evidence of switch loading.
This is Ryan. I'm sorry. I was going to say this is Ryan.
Go ahead, Ryan.
Okay, and in the 2016 EPA study, we found ethanol, I believe, in 90% of the 42 samples. But as a caveat, we could not identify if that ethanol was created chemically in the tank by some reactions, but the overall assumption is that it probably came from switch loading.
That Ryan already did, but just for those who may not be familiar with the term, what switch loading means is if one compartment in a truck carried diesel fuel one day, they obviously empty it, but there's always a little bit of residue left. The next day, if they transport some gasoline, they're mixing a very small amount of diesel fuel with the gas, and that can go, any one of, a bazillion different directions. But that is one of the, we believe that's probably the primary way that we get small amounts of ethanol in diesel fuel, when, of course, there should be none. And I'm certainly not an expert on the chemistry, but I'm not aware of any obvious chemical reaction that would take pure diesel fuel and then you'd end up with ethanol in it. So switch loading seems to be the most likely source for that.
Thanks, Ted. And this is Ryan Haerer again. I'll say one more thing is I believe the state of Georgia, David Au and their research labs down there with some others has done some work on testing the flash points in diesel fuel after short distance transport and has found reduced flash points. And so we can find the data and share it with NEIWPCC, find the research, but it has to do with the evidence of that switch loading Ted was just talking about.
Awesome. Anybody else? Alrighty. So the next question, have they thought about collecting information about sites that have no corrosion? That's good info too.
I think it's a fantastic idea, but the truth is we haven't looked into it in Vermont.
Yeah, I don't know that the Emerging Fuels Task Force has specifically called that out in any of the, clearly not in the reporting tool. I was just looking through the survey really quickly to see if anything there might address that. We do ask for, in one of the questions, we ask for sort of a range of percentage of facilities where you see no to minimal corrosion. So we kind of lump those together in our survey questions. So it's a great question, and that's probably where we'll capture that rather than having a bunch of pictures of clean, pristine-looking equipment.
This is Chris. A follow-up on that. One thing we are planning to do here in Arizona is expand our study to look at schools that have taken advantage of some of our state programs to install new UST systems on site and follow those new pristine systems to determine, how long does it take for a tank to go bad, or under what conditions do we start to see this corrosion emerge or not emerge, and especially being that these new tanks, this new infrastructure will have only ever been exposed to these emerging fuels rather than starting out under conventional and then going to storing emerging ones. So hopefully we'll have some good information emerging from that as well.
Data, or would service providers, third-party inspectors, testers, installers be helpful? And Doug, you might have already answered this question, but I'm not sure.
Yeah, I think I did. We would love to have information from whatever source. All of those we have the ability to accept, and whatever is submitted, we vet, so we can assure the quality of the information we're putting out there. But absolutely, if some of our industry stakeholders have information to share, we'd love to see it.
All right, there's a couple more questions here. If any other folks have questions, please feel free to enter them into the chat box on the right. The remaining questions are, why isn't the ethanol in diesel included in the results? It's a follow-up to this second question.
Oh.
So the question again is, why isn't the ethanol in diesel included in the results?
So this is Ryan. I'll take this. I think this may be related to the second question, but to the Arizona study. But in the 2016 EPA study, we did report on it was a study about diesel tanks only, so we were surprised to find that level of ethanol. So that's in the results. That emphasis to look for ethanol came from the 2012 study that was done by the Clean Diesel Fuel Alliance. That study was not intended to, it was intended to generate a hypothesis for further investigation, and that hypothesis that came out was that ethanol was the leading cause of the corrosion. So we looked at that in the 2016 study, but we also looked at other factors. And then I'll leave it to Chris or someone from Arizona to answer from there.
So this is Chris. Yeah, we didn't delve into the fuel quality results on these slides specifically because it's a really complicated issue right now of knowing that fuel degradation by microorganisms and general chemical reactions is a specific set of processes that ultimately result in tank corrosion and degradation, but it's not a direct one-for-one. It's not that if you just have a snapshot of bad fuel quality that your tank is automatically going to be corroded. We have evidence of severely corroded tanks with fuel that passes standard inspection analyses, and then we also have the converse example of tanks that we would consider very minimally impacted, but also having very fouled fuel. So this is an area where a lot more research is needed to understand what takes place between that relationship of fouled fuel and deteriorated tanks.
Let's see. Do any of the pre-1981 single-wall fiberglass tanks have independent laboratory listings for ethanol fuels? E10, et cetera?
This is Ryan Haerer from EPA. I'll take this one unless somebody else wants to jump in. But both of the companies, Xerxes and Containment Solutions, who was formerly Owens Corning, have put out letters about clarifying the compatibility of those early age tanks. All tanks and piping today produced are compatible with up to 100% ethanol. In between today and 1981, and actually in between 1981 and kind of the mid-90s, I think, there was a phasing in of bringing those tanks up to compatibility standards as the fuel system changed. So long story short, prior to 1981, none of those tanks, I believe, were designed for or warranted for use with any blends of ethanol in them.
This is Tara. It's also important to note that if you go to the compatibility tool on the ASTSWMO website, you can pull up those letters that Ryan just referenced.
Oh, perfect.
All right, here's an additional question. Does cathodic protection provide reduction in corrosion with emerging fuels?
This is Ted, and the quick answer is no. Cathodic protection does a good job of preventing corrosion on the exterior of the tank. That's where soil is in contact with a corrodable material like steel. But unfortunately, cathodic protection, at least the conventional cathodic protection of, let's say, a STIP 3 tank, does nothing to protect the interior of the tank from whatever substances may be formed from the breakdown of some of these emerging fuels. I don't know if anybody else can add to that.
I think you nailed it, Ted.
Excellent. All right, here's another question. For the corrosion observation tool, how do you avoid sampling bias? I could see most people only documenting severe corrosion.
I can take that one. I think the point of the tool isn't to get a comprehensive list of how many tanks fail and how many tanks don't fail. The process is trying to document what we're seeing out in the field, maybe a little less quantitatively. Yes, it's a problem, and here is what we're seeing and why it's a problem. And then moving forward, studies could maybe look at some of those finer details. So we're not getting into minutia here. We're looking at broader observations that we're hearing about anecdotally that we want to be able to document a little more clearly.
This is Ryan. Just to build on that, I think, from the federal perspective, we talk about, that data that ASTSWMO can gather that we just don't have with this tool. I think you can pick up a lot of things, as Doug was just saying, where even if it's not quantitative, you can pick up on trends. And one example is the diesel corrosion. Generally, we hear about it in a lot of the country, but anecdotally, we also hear that New England may not have as much of it. So you ask, is that the weather? What's going on? So you look at maybe the upper Midwest or something, which might have a similar cold climate, maybe has to do with the weather, but they do seem to be having the issues. So something like this, is an opportunity to really help expand, even if it's not quantitative, and even if there might be some bias in there. Sometimes just observations of what is happening can be really helpful. So thanks. That was a great question.
All right, here's another one. Is there any correlation between tank top sump corrosion and interior tank corrosion?
So this is Chris again. That's a really interesting question. So far in our study, we have not seen any, but that's definitely an interesting point.
And this is Ryan. I'll add there. Generally, this is very general, but anecdotally, what you hear is that you see the tank top corrosion in gasoline ethanol systems, and you don't really see as much corrosion inside of the tank in those systems. And then generally, you could look in the system, you know, at the same station right next door that's storing diesel, and what's in the tank top sump would generally be pretty clean. You wouldn't see much corrosion there, but you might see a lot of corrosion on the inside of the tank. So that's one relationship, but, you know, again, the studies like Arizona is doing is really trying to drive into that data, as well as the tools that we're talking about today. The other thing we hear, which is a little bit of a different relationship, but within that gasoline or ethanol, where you often see that corrosion, if you're talking about the relationship, sometimes we hear, and the state inspectors will be able to speak to this, but the pressure, the vapor pressure from inside the tank and the leaky seals, sometimes on the fittings on the bottom of the pumps, somehow ethanol is getting into the sumps and allowing that corrosion to happen in those gasoline ethanol systems. And there has been a published report on that, I believe in 2013 or 2014, from Dr. John Wilson from EPA. And he published that in the Petroleum Equipment Institute newsletter, I believe.
Alrighty, here's another one. Was there any correlation seen between tank throughput and corrosion? If a tank is sitting idle with lower volumes versus tanks that are fuller and constantly having new fuel?
So this is Chris again. We didn't look specifically at throughput. I will say, however, that throughput will have an impact or at least influence on fuel fouling, and then thus that eventually ties in with tank degradation. As to what that's going to look like and what that relationship is, we don't have that information yet. So stay tuned, and we'll see what we can come up with as our study continues.
Here's another one. Would nitrogen flush improve corrosion resistance?
This is Ted. I'm not an expert on this subject, but I would have to assume, since so many of the known paths of corrosion involve reactions with oxygen, if you somehow found a way to displace the oxygen, my guess is that you'd probably see reduced amounts of corrosion. But I'm getting out of my area of expertise. I probably should have just remained silent with that question. I'll let others who know more take it from there.
So this is Chris again. Yes, you will see a change in the corrosion rates depending upon specific corrosion mechanisms. So just like Ted mentioned, if they are active mechanisms that require oxygen and you displace that oxygen, the observed corrosion rate will be decreased. However, there are alternative corrosion mechanisms that are not dependent upon oxygen. And so if the tank conditions are favorable to allow those mechanisms to be present, then those will be active at whatever rate they are supported. So a lot of it will come down to fuel chemistry, and especially down to water chemistry as well. As a perfect example, if you have marine influence water, so if you had a coastal flooding event and you had marine water that came into contact with fuel in a tank, and you displace all of the oxygen, that's a very favorable environment for sulfate reduction and sulfidic corrosion that is very commonly observed in marine industry types. So it's going to be very dependent upon the scenarios there.
Alrighty. Is there any information regarding the first components of an US system that first show evidence of corrosion?
This is Ryan. I would have left this up to the states, but with diesel, where you can't see it inside of the system, generally you might find slow flow and plugged filters might be a sign. And then the PEI study from 2012 that Chris talked about, the sampling survey, often we hear about corrosion on the submersible turbine shaft, but of course you're not going to be seeing that unless you're pulling that for servicing. In ethanol gasoline, you can just see it under the sump. But what do the states have to say about that?
Yeah, in Vermont, we have not seen any one particular part of the S system or any one component that starts to, that's sort of like the canary in the coal mine. It's the first warning sign. As Ryan said, we commonly find evidence of corrosion in gasoline systems in the tank top sump. And because we don't routinely look inside diesel tanks, we don't really have a good sense of how severe the problem is with ultra-low sulfur diesel tanks. But it would be nice if there were one component that you could keep checking that would sort of be the first warning sign. That's a great question.
Maybe that can be in addition to your submission on the corrosion reporting tool. If that was the first thing you said in your notes, this was the first item we saw. If you happen to be reporting many things.
Yep, good point.
So here's one. I believe this is a clarifying question. So are there FRP tanks in use today that should not even be using E10?
This is Ryan. I'll just say this. Yes, absolutely. There are certain states, Missouri, I believe, is one of them. I don't know of any others yet, but have required states that cannot determine compatibility with E10 to remove those tanks. And Ted, I'll let you talk about New England and what you guys are doing there just with older tanks generally.
Yeah, most New England states have some sort of a deadline. In Vermont, for example, we had a phase-out schedule for single-wall tanks. Vermont has required all new tanks installed since 1987 to be double-walled. So we have very, very few single-wall tanks left, and the few that are remaining in operation in Vermont have all been lined. But I think all the other 5 New England states all have some sort of a deadline that's prompting the tank owners to pull these older tanks. So the good news is that here in the Northeast, there are very few pre-1981 tanks that remain in the ground.
Alrighty, here's one more. If there are any remaining questions, please enter them now. This is the last one that I've got. Is methanol ever an optional fuel component?
I haven't heard of it being added to fuels. Anybody else know anything about methanol?
No, we haven't heard of it. This is Chris. We haven't heard of it being used as a fuel oxygenate here either.
Yeah, we've never seen that in Utah.
I would assume, since methanol is so volatile, that if you added it at, let's say, at the bulk plant, there's a good chance that a lot of the ethanol would have evaporated out by the time it got to the gas station. And then I would assume that a lot of the methanol would evaporate into the ullage space. So my guess is it really wouldn't be well suited as an oxygenate. Don't know.
Yeah, this is Ryan Haerer at EPA. So with methanol, it's definitely a regulated substance, and so if you happen to be storing it, just like any of these other fuels, our definition of what has to have compatibility and meet all the regulations, as well as in all the states, has to meet all the regulations of a underground storage tank system. It's not specific to fuels; it's all regulated substances. But I have not heard of. I think methanol may have been older, may have been used in the past, but I don't hear it, just like the guys just said now, have not seen it, but I think it has been used in the past. But realistically, that is a question for at least at EPA, kind of the other half of EPA, which writes the fuel standards and regulations. They handle all of that, and they would be the experts, so I would have to defer to them.
Alrighty, we did get one more question here. Has fuel treatment, in parentheses, diesel bug additive, been shown to affect an UST system?
This is Ryan. I'll take this one and let the other people chime in, but I don't know that there's any data on that. But what I do hear anecdotally is recommendations, and some of the organizations have also put out, thinking of the Coordinating Research Council, I think Coordinating Research Council's, I believe it's document 671, put out a 2-page guide about operating and maintaining diesel tanks for best practice. It's kind of intended to be put up in a store for people who are not specialists in fuel, but it's kind of, hey, what's the best way to maintain our tank to reduce the chances of corrosion? I think in there they mention, using, some kind of a microbial treatment. We hear that a lot anecdotally, but I don't know that there's any data at a national level to the efficacy of that.
Well, again, just a big virtual thank you. I'm sure everybody listening in is clapping right now. But again, I'd like to thank Ryan, Ted, Doug, and Chris, as well as Tara on the line. Thank you all very much. Additionally, you should have a survey popping up after the webinar, after you close out. So please fill that out. Hugely helpful again. And there's an opportunity there to get credit for your attendance. Additionally, with that survey, we're interested in obviously what you thought about today's webinar, as well as future opportunities and any difficulties you might have had with logging into the webinar and things of that nature. Again, these webinars are posted on the NEIWPCC webpage. And if you have any questions regarding this or future trainings, please contact Drew Young. I am simply filling in for him today. And with that, I'd like to thank our presenters again and wish you all a wonderful rest of your week. All right, take care.